we welcome Wasuwee, Sonic's lead testing engineer. Let's get some technical talks here going. Welcome on stage. It's all yours.
Yep. Thank you, and thank you for your kind introduction, and thank you for having me today. Yesterday, some of you may have heard presentation from Bernhard. He gave you a sneak peek on how we can make Sonic super fast. And for this talk, I want to show you from a different angle. I want to show you from a testing angle. And from this talk, I hope that you get that reliability has always been our priority. And from the beginning, we want to design Sonic to be safe and reliable for everyone to use. So I just want to show this slide again that Bernhard mentioned yesterday, what Sonic has achieved. So far, Sonic has been very fast. It achieved sub-second time to finality. It achieved over 100 million transactions per day, while it used so small of the storage. And all this, we are still 100% EVM compatible. We achieve all this not through tweaking client code, but we achieve this through a thought-out design with reliability in mind. So I believe that the trust in blockchain in L1 we can build through having high security and high level of functionality. So say that you want to send 100 transactions in Sonic. You want that all 100 transactions to be processed correctly. 99 transactions would not be acceptable in this case. What does it mean by have reliable chain? Having reliable chain here, let me recap on how a transaction is sent to the chain here. So if you send any transaction, it will go through web interface, which actually go through our RPC interface. And then it get into transaction pool. And from there, it actually get ordered through consensus before it get processed by block processor. And there, your balance will get stored in the database. And understanding potential risk in any of these components would be key to make a reliable software. So just want to give you some of example risks that you get if we have a poor design consensus. If we have any loophole in consensus, then we leave a room for a bad actor that at some point, they may take over the chain and create a new fork, have their own rules. And if it gets to that point, your asset would be not safe on the chain. For block processor as well, if we have a faulty block processor, it means that I know that some of you are the app developers. And when you deploy your app, you want to deploy on multiple EVM-compatible chains. So if your app works on one chain and not this chain, is not good. It means that your smart contract may be executed not as you design, and whatever gets stored to the database may not be what you want it to be. It also means that your assets could be at risk again. Our engineer actually thought of a lot of ways on how we can minimize the risk of the chain getting compromised. And through this, we adopt so-called defensive programming. Here, we actually develop a lot of very comprehensive testing so that we can find more bugs through the development. And when we fix more bugs, it would also mean that the chain become more and more secure. We deploy so-called multi-stage testing. And this is an industrial standard. This means that this is not something innovation, but this is something that every software company should do. So if our developer commit a new change, a fix to a bug, then it would first go through so-called continuous integration tests. And this would consist of unit tests, code coverage and linting. This test will be something very quick that can be done within 10 minutes, and will give feedback to developer right away. So within 10 minutes, developer would know that the fix is working as intended, or it has to be improved somewhere. And if the change is good, it gets merged to main branch, and every night we would have a lot of changes every day. And all these changes get bundled together, and we do another test, more extended test. It's called nightly test. Here, we not only do just unit tests, we would do integration tests, fuzzing, race detection, and so on. And once we have, once we complete features or want to release bug fixes to the public, we go through another level of testing, which is called release testing. This is the most extended one, where we include whatever we had before, and we also do end-to-end testing. What mentioned here is as industrial standard. This is nothing special, but it's also said that we also care about testing, that we have to go through all this trouble again and again. When I first joined Sonic around 3 years ago, I was assigned to work on testing, and to be honest, it was not so easy. This is because there are not a lot of tools around that we can use for testing. There are a lot of challenges. The first challenge that I want to mention is that blockchain execution is stateful. What does it mean here is that if I know that there is something wrong with my StateDB when I try to process transaction 100, I actually need to process everything from transaction 0 up until transaction 100. So I have to process 100 transactions just to get to the point where I want to be. And this can be very slow. And thinking that Sonic right now have 48 million blocks and 100-something million of transactions, if we have some problem at the end, we have to start from the beginning, and this is not good for testing. So this is a work from Phantom together with Yonsei University in Korea. They designed a data structure called substate. This is a minimum information needed to process one transaction in isolation. So it has information in the state, transaction itself, so it knows just this minimal information, we can actually process any transactions. So what we need to do is that we need to record substate for the first time, and then we can run any of this substate inside of our IDA framework. So transaction 100 has a problem. We have substate recording of transaction 100, then we can just run that one transaction again and again. So this will improve our development cycle quite a lot, so that we can actually have Sonic finished within 3 years when we started. There would be another good example of how we use IDA framework. Because substate here, we can record from any EVM-compatible chain, which means that we can record substate from Phantom, we can record substate from Sonic, and we can record substate from Ethereum mainnet, Ethereum testnet, and so on. And this gives us a lot of data set that we can test and make sure that our block processor works as we want it to be. So for example, recently when we developed Prague fork for Sonic, we developed during the time when Ethereum did not release Prague yet. So basically, we don't really know how actually Prague transaction would look like. But Ethereum would release Prague fork in testnet first, so that we can do testnet recording, and then we already have the real-life example of how Prague fork would be used, how Prague transaction would look like, and then we can actually test it with our system and know that our system supports Prague. Another example, another challenge that we have when we do testing would be that we have the claim that our client, the Sonic client, is 100 EVM compatible. But how can we be sure that it's really 100% compatible? Our engineer implement so-called conformance testing. And conformance testing here do really hard implementation on extracting formal specification from Ethereum specification. So we actually formalize EVM instruction into formal spec. And from there, we can actually use formal spec to generate micro test cases where we can actually use any input, valid input, and in combination with instructions, and generate millions of test cases, including corner cases. And if we run these test cases with our system under test, in this case is Sonic VM, if it produces something that's not equivalent to Geth, then we know for sure that something is wrong with our Sonic VM. And through this approach, actually, we have discovered a lot of corner cases that we didn't think about, and we were able to fix them in time before we deliver Sonic to you. Another tool that we have to develop ourselves is called Norma Blockchain Simulator. So our challenge here would be that we want to have a rare scenario that unlikely to happen in blockchain, but we want to run that, test it, make sure that our chain would behave as we design. And we want this to be in a controlled environment. So we did this through containerizing every of our client into a Docker and run off them on a Docker network. Through this, we can run off this in a single machine. And we also create an artificial application where it actually generates test cases and feed it to the network. So actually, through this approach, we can write any scenario that we want. Norma, the driver, will set up the scenario and create Docker containers, run the network, and see the result. So the rest scenario that I mentioned here would be something like network forking. So if we have a hard fork, will our network eventually reach the quorum? If we have a new version of Sonic, add to the network, can it communicate with the older version? Or what if network has a blackout? So let's say 2/3 of the network somehow get blacked out. What would be the reaction from the chain? And more. So these are only some of the tools, the notable tools that we have been using so far, but there are even more that we try to do with testing. We have been using more and more of formal method to prove that consensus works as we designed it. And we also use more and more of stochastic and Markov chain to explore the behavior, how actually users use our chain, what kind of operation have been heavily used by processor. And through this information, we can optimize specific operation that we know that has been used frequently. And through all this, I hope that I can give you a bit more confidence that if you use Sonic, Sonic is actually safe by design. And with all the achievement that Sonic have shown here, it's actually built with reliable in mind. And thank you for your attention.
All right.